This lesson is an introduction to waves. A wave is made up of oscillations that propagate through a medium. Remember that oscillations are back and forth movements. And each oscillating particle, because it's connected to the next one in line, is going to pull on the next one. This is a simulation from PhET, and here we've got a string that has no end, and it's connected to this machine, and I'm going to send a pulse through. So this is not a wave yet, this is just a pulse. But notice how as it goes up and down, each particle pulls on the next particle, and it goes up and down. Now I can set this to oscillate, and so if the source is oscillating backwards and forwards, each particle pulls on its neighbor and starts it oscillating backwards and forwards. And if we have no end, we just see this wave motion that's moving off to the right. Now notice a couple things here. First of all, that the source is oscillating sinusoidally, and so all the particles are oscillating sinusoidally as well. We see this sine-shaped curve. Also notice that we definitely see something moving off to the right. You can see this disturbance propagating out the window here. But if you focus on the green dots, you can see that each individual particle is actually just moving up and down, and it's not moving left or right at all. The particles are moving up and down. The disturbance, the wave, is moving off to the right. So again, a wave is made up of oscillations, and those oscillations are propagating through the medium. In that case that we just saw, the medium was the string, but the particles themselves are not actually propagating through the medium, they're just moving backwards and forwards. Now we saw that if the source was oscillating with simple harmonic motion, like it was in that example, then it makes the neighboring particles oscillate with simple harmonic motion as well, and the wave that we see is going to be sinusoidal. And we saw it sinusoidal in space there, that's what we were looking at, but we could also look at each individual particle's oscillation as it was going up and down, and we would see that it is sinusoidal in time as well, and we'll get to that in more detail in a moment. So that's an example of a traveling wave, and traveling waves transmit energy, but they do not transmit matter. Again, we saw that the particles themselves, the beads on that string, were not moving out the window. They were just going up and down. But there was a disturbance that was moving out the window. And that disturbance, that oscillation, carries energy, or the ability to exert a force through a distance and make the neighboring particles move. So traveling waves transmit energy, but they do not transmit matter. Now, we said above here that we can talk about waves in terms of time and space. And so we're going to graph displacement of the particles on the y-axis, and we can graph either of two things on the x-axis. In this first example, I'm going to have distance. So this means distance along the string. So from left to right, like what we were seeing. In the second example, I'm going to graph displacement. Again, this is the displacement of the individual particles on the string up and down as they oscillate up and down like that against time. So here's two possible graphs, one displacement distance, one displacement time, and you'll notice that in this case they look exactly the same, and they can look exactly the same or they can look different, but it's important to recognize that what's on the x-axis is different. This is distance, so that's measured in meters left and right along the string, and here we've got time measured in seconds. So this graph is showing us what we were actually just looking at when we looked at the string. This is a frozen snapshot in time of the whole string. So this is a frozen snapshot as we go from where the oscillating motor is moving up and down here across the string, and this is what we saw frozen in time. The displacement again is the displacement up and down of the particles on the string, whereas this one is the displacement in time of a single particle. So let's say I focused on this particle here, and the wave is moving off in that direction like it was in the video. A moment later, this particle is going to be there, and then it's going to be there, and then there, like that. And so slightly in the future, this is, let's say, time 1, time 2, time 3. And so that's what we're seeing over here. The particle is there, and then at time 1, it's moved up, at time 2, so 2 seconds into the future, time 3, etc. So it's kind of moving in that direction. We are watching the history of what is going to happen to this kind of going into the future. It's sort of a backwards history, if you will. So that would work for this point. If we were looking at, let's say, this point here, then a moment into the future, if the wave's going this way, it's going to be downwards. And so you can work that through and see that the graph will also be sinusoidal, but if we're dealing with this point, it's going to be flipped upside down like that. So displacement distance and displacement time graphs are two different ways of thinking about the same thing. And we could actually draw a displacement time graph for just a pendulum or for a mass oscillating on a spring, because here we're just looking at one individual particle. You can't draw a displacement distance graph for these things because there's no horizontal distance. Just like when we talked about simple harmonic motion and pendula and masses on springs, we can talk about frequency, which means, in this case, the waves per second. And so if you were to stand here and watch the waves go past you, the frequency would be how many waves you were counting in each individual second. If you counted 2 waves in a second, that would be a frequency of 2 hertz. If you counted 100 waves in a second, that would be a frequency of 100 hertz, 100 cycles or 100 waves per second. Whereas the period, which again we give the symbol capital T to, is the time for one cycle of the wave. So if you time how long it takes for a single wave to get past you, that's working out the period. Now, if you look at these graphs, there's a few other things you can get. The distance from the peak to the baseline, or from the trough to the baseline, that's the amplitude, A. And that amplitude in a traveling wave is going to be the same for all the particles, and so we'll get the same amplitude no matter which of these graphs that we look at. So A is the amplitude, the distance from baseline to crest or peak, or to baseline to trough. On the displacement distance graph, if we take 2 of the same points from a wave, so here crest to crest, although we could go trough to trough, then if we go from one to the next, that's the wavelength, and the wavelength we give the symbol lambda to. So lambda is wavelength, and it's how long one single wave is, and it would be measured in meters. Correspondingly, on the distance time graph, if we want to know how long a complete cycle is, we would look from one crest to a crest. So let's just take the red graph here, from there to there. That would not be a wavelength because we don't have meters on the x-axis. That would be one period, t. So the amplitude will be the same, but we get the wavelength from one graph and the period from the other. And of course, we can work out the frequency from the period because they are related as reciprocals of each other. So that's the 2 graphs. Now that we've got the idea of frequency and wavelength, we can combine them to get what's known as the universal wave equation. So let's do a quick derivation. We know that average speed is equal to distance covered divided by time. So if you think about how much distance is going to be covered in one period of time, let's set the time to 1 period. By definition, 1 period is the amount of time for one cycle, or for one wavelength to pass. So the speed of the wave is equal to the wavelength divided by the period. And because we know that the period is equal to 1 over the frequency, therefore 1 over the period is equal to the frequency. And so this rearranges to give us f lambda. Lambda again being the wavelength. So this is our universal wave equation. The wave speed is equal to the wave frequency multiplied by the wavelength. Just to note that the speed is going to be determined by the medium, what substance the wave is propagating in. And the frequency is generally dictated by the source, what's oscillating. So the frequency is going to tend to stay the same because each particle is going to act as a source for the next particle. I often refer to that, and you'll hear that in other places, referred to as the handshake principle. So the handshake principle will tell us that the frequency will tend to stay the same even as you move to a different medium. Even as the speed changes, the frequency will stay the same because each particle is acting as a source for the next oscillation. It's oscillating backwards and forwards and shaking hands with its neighbor. So if you can think about the frequency staying the same, as the speed changes, let's say the speed goes up, that means that the wavelength is going to have to get longer. And if the speed goes down, the wavelength is going to have to get shorter. And we'll see that effect in future lessons. Also, just to note that the speed of the wave is not the same as the speed of the oscillating particles. They can travel at different speeds, and in fact, they're often moving in different directions. What we saw in the simulation was the particles in the string oscillating up and down, but the wave, the disturbance itself, moving from left to right out the window. So that's an introduction to waves and the terms that we use to describe them.